Well, now we would like to establish our main connection between our potential function and the electric field. We have two results. Our first result is a mathematical result, which tells us that the change in our potential function is equal to the line integral of a to b of the gradient of that function dotted into some displacement. And this was the fundamental theorem of calculus. Now, in physics, we defined the difference in our potential function as equal to minus the integral from a to b of the electric field dot ds. Remember, what we said there was if we have a point B and we have a point A, and we take our test charge and we move it from A to B, and we calculate the work done by some type of electrostatic interaction, and we take the negative of that work and divide by the test charge, that's the physical meaning of this potential difference. So this is physics. And now what we'd like to do is do a little mathematical physics. We'd like to set these two quantities equal, and you can see the integrands must be equal, and that's our key result, that the electric field is equal to minus the gradient of the potential function. And this is a key way of recovering electric field from potential. It also tells us, recall that the direction of the potential is to higher, of the gradient is to higher potential, so the electric field points to lower potential. So the direction of our electric field is towards lower potential. And that's a conceptual way to think of a lot of electric fields for various sources that we'll look at. Let's consider some application of our concept that the electric field is equal to minus the gradient of the potential. We calculated the potential for a ring along the axis that passes perpendicular to the plane of the ring. And let's say the ring has a charge q. The radius of the ring is r. And we'll take our field point P here, which was a distance z away. And for this particular problem, we calculated that the potential at this field point was equal to 1 over 4 pi epsilon naught q over z squared plus r squared to the 1/2. Now, we can use this result because we have the potential entirely along this direction. And if we wanted to find the electric field along the z-axis, and this is just along the z-axis, then in that case, the result, we can apply this result. It just becomes a simple, in general, the potential has a variety of terms in it because it's the gradient of the potential with an overall minus sign. But in this case, it reduces to a one-dimensional calculation, dvz dz in the k-hat direction, because we're only looking at changes along this direction. And that's an easy function to differentiate. We have the minus sign on the outside. When we differentiate 1 over z squared plus r squared to the 1/2, we get a minus 1/2. We have the constant 1 over 4 pi epsilon naught. We have q over z squared plus r squared to the 3/2. And upstairs, we have a 2z. And so what we have for the z component of the electric field over the axis, we have the 2's cancel. We have our constant 1 over 4 pi epsilon naught qz over z squared plus r squared to the 3/2. And that is a simpler calculation than setting up Coulomb's law and taking vector decompositions and throwing away the alpha-axis components and then calculating the electric field along the z-axis. It's another way to calculate the electric field.
OK, in a previous video, we did this problem. We walked through it slowly and carefully. We had 3 charges, minus q, plus q, and we said, what's the potential at P relative to a reference point at infinity, and what we found was that v of p relative to v of infinity had three terms: the potential from this charge, the potential from this charge, the potential from this charge, and when you added them up, we got minus kq over a. So we worked out v of p. And I pointed out at that time that that was actually kind of, in a sense, useless, because if all I know is the potential at this point, if I only know the potential at one point, I do not know what the electric field is at that point. So from just this information at the bottom here, if I ask you what's the electric field at the point P, you can't tell me. So how do I get the electric field from the potential? Well, we now know if I want the x component of the electric field, that will be minus dv dx, or the y component of the electric field, that will be equal to minus dv dy. And so you know that to take a derivative, it's not sufficient to know the function at only one point. You have to know the function in a region around that point. And only when you know the function in a region around that point, you can take the derivative. So I have to know the slope of the potential function around this point, not just v at one point p. So to finish the story, I'm going to actually walk you through the logic of how to calculate the electric field at the point P, starting from the potential. But it's not enough to know v at only one point. We actually have to start with v at any x and y. So let's pick a generic. What I'm interested in is the electric field at the point P, but let's pick some generic point x and y and ask what v is at a generic point x and y, and that will give us information about v in an entire region around the point P. So v at a point x and y, again, we'll have three terms. I'll have a minus kq divided by the distance between the point xy and this point, and that will be the square root of x plus a squared plus y squared, because the distance from this point to here is there's an x component that's an x plus a, there's a y component that's just y, and so the distance is this square root. Then I have a potential coming from this charge, and that will be minus kq divided by just the square root of x squared plus y squared. And then I have this potential, and that will be a plus kq divided by the square root of x minus a quantity squared plus y squared. So this expression is the electrostatic potential anywhere on the board. If I want to know the electrostatic potential at the point P, well, then I could put in 0 for x and a for y, evaluate this, and I would get the answer that we had before. But I would then, if that's what I do, I only know the potential at one point. That's not what I want to do. That would be a mistake if what I'm trying to do is get the electric field. Before I plug in the location of the point P, I'd better differentiate. So I need to evaluate Ex. I need to take the derivative of this with respect to x. And I'm going to do that, and I'm just going to tell you the answer after the dust settles. But anytime you do something like this, you should ask yourself what you expect. So let me ask myself, at the very least, what sign should I expect? So what direction should the electric field point in at the point P? Well, let's think about these three charges. From this charge, I'll have an electric field pointing this way. From this charge, an electric field pointing this way. And from this charge, an electric field pointing straight down. So Ex should be negative. So I then go and do some calculus, which I'm going to spare you. And but when I do all that calculus, I get a lengthy expression, which I think I will spare you. It's negative. It has three terms. And after I've done that, and only after I've done that, then I can plug in x equals 0 and y equals a. And when I do that, I get minus kq over square root of 2 times a squared. Similarly, for Ey, what do? I do minus dv dy. I take this long expression, differentiate it with respect to y. I'm going to get a big messy expression. What should its sign be? Well, let's think about the electric field in the y direction. From the two outer charges, this one pushes an electric field that way. This one pulls an electric field this way. Their y components cancel. But then you're left with this middle charge, so I expect an EY that's negative also. And in fact, I get some big long expression. I then plug in x equals 0, y equals a, but I plug that in only after I've differentiated, and then I get minus kq over a squared. And so what I learn is that the electric field at the point P has a negative x component and a negative y component, and the y component is a bit bigger than the x component, so the electric field at this point P is a vector that is pointing kind of in this direction. And if all I knew was the potential at the point P, I would have no idea. Because the potential at the point P doesn't tell me the electric field by itself. To get the electric field, I need to know how this potential function slopes. So I need the whole potential function, which I then need to differentiate, do some calculus, and get an answer which tells me the direction that the electric field is pointing.